Okay, so this is lecture number 40 of E503, and we have covered most of the topics that we would like to cover in this course, and this is the last week, so we have only 3 lectures left. So in these 3 lectures I will discuss 3 topics essentially. First I will discuss ergodicity, then I will discuss blue estimator, based linear unbiased estimator. Okay. Then I will discuss KL, Calhoun-Loewe transform. Okay. So we have 3 lectures left, and we have 3 topics to discuss. So today we are starting with ergodicity. Okay. Ergodicity. So let me write a comment about this. In our earlier discussions, we have made use of moment information of stochastic processes, of, let's say, random processes, okay. In practice, mean, autocorrelation, and possibly other moment properties of a random process are not known a priori. So no one is giving us information about the mean function, autocorrelation function, etc. So they are not known a priori, but they have to be estimated from, let's say, data. Okay? So that is the issue. So how can I estimate, for example, the mean function or the autocorrelation function from the data? That becomes the topic of essential ergodicity. So let me write the first topic, mean-ergodicity. Or this is also said as ergodic in the mean. Ergodic in the mean. Okay. So what do I mean by this? Let's assume that x of n is a Weissan stationary process. Okay. So what does that mean? If x of n is Weissan stationary, I know that the mean function, expected value of x of t, mean function in discrete time, x of n, is just constant. Okay, I know that it is constant from the Weissan stationarity information. I have just that. Now the question is how you would estimate this constant value, mean of the process. So an estimator for the mean mu x can be mu x of x, so 1 over n, and 1 to n, let's say, x of n, okay? Or let's start from 0 to n minus 1, more signal processing notation, okay? So previously we have studied this one, and we have called this, maybe you can remember, sample mean, okay? So I have some samples, n of them, and I'm calculating their average. Okay, this is the sample mean. So this sample mean has some optimality properties. So remember that in maximum likelihood estimation that we have discussed at the beginning, maybe at the beginning of the estimation topics we have discussed this. In maximum likelihood estimation, we have derived sample mean, this estimator, as the optimal estimator for the following problem. For the parameter estimation of C parameter in the following setting. Okay. So I'm assuming that x of n is C plus W of n. It was, I believe, something like this. N is equal to 0 up to n minus 1. Okay. So these are observations. Okay. So C is just constant. And this is something like this, I guess. And IID. So noise is Gaussian distributed. It is IID. Right now we have much more information. So this is white noise. And I have a white noise plus a constant at every observation. Okay. So in vector form, again, we are more experienced. This can be written as vector 1 plus C times, let's say, a W vector, isn't it? I can say things like that. So this problem is different from, Wiener filtering problems. The reason it is different is, now this C is non-random. So this is a non-random parameter. In Wiener filtering, if this is the desired C, let's say, then it has a, let's say, variance, it has a mean value, it's cross correlation with the, the observations are required and so on. Okay? But this is a non-random parameter, meaning that there is no probabilities associated with this parameter. So this is the reason that this is maximum likelihood estimation, non-random parameter estimation. It's not a Bayesian estimation result. Okay? So we have derived this sample mean, this result, so this becomes C hat in this case, as the maximum likelihood estimator. And at that time we have discussed the bias of the estimator, consistency of this estimator, efficiency of this estimator, and so on, at the estimation theory topics that we have covered. Now the question is, I'm using the same estimator, but as you see, this is just, I have picked up this to estimate Ux, and I have no idea whether this is a Gaussian process or whether this is IID Gaussian and so on. Okay, so whether this is noise part is white noise or so on. So what do I mean? So question is, if mu x of hat approaches this mu x as number of observations goes to infinity, okay, then the process is said to be mean-ergodic. Now here's a question. Now this is a random variable. Okay, let me write this question. So how can we justify the convergence concept for the random variable mu x? Okay, because convergences is a topic of, you may say, the calculus. But if I have random variables over here, if the number of observations that are combined to form this random variable is increasing, then how can I justify this convergence, the word convergence? Well, then let's be more specific. The answer for mean ergodicity, this is a topic in random variables actually. Convergence in mean square sense is let's say taken as the definition. Okay, so for mean ergodicity, we have the following. We need, so for mean ergodicity, we need, number one, expected value of this random variable estimate approaching mu x to true one as n goes to infinity. Okay. Number two, the variance of this error mu x minus mu approaches 0 as n goes to infinity. Actually, this is what we call the consistency, isn't it? So this is unbiased estimator, and this is a consistent estimator. Again, we have introduced these concepts in the earlier lecture about estimators and their properties. Okay. Now the question is, well, how can I examine the performance of this estimator for an arbitrary wise and stationary X process? Okay. So is it a unbiased estimator or a consistent estimator for an arbitrary wise and stationary process? Is the main point of this discussion on ergodicity. Okay. So then let's analyze this. So let's study the mean ergodicity of arbitrary wise and stationary X of n processes. Okay. So let me number one, unbiasedness condition. So what is that one? Expected value of mu x, is it equal to, let's say, this as n goes to infinity. Okay. So I'm right now studying this argument, which is the first one. Okay. But let me write this. Okay. Then expected value of mu, this one is expected value of 1 over n x of n 0 and minus 1. And we see that this is nothing but summation of 1 over n and 0 and minus 1. The expected value of x of n is mu x. So this is equal to mu x, and that is it. So clearly, for all n, this is equal to mu x. So independent of the number of the observations, I always have, this on the average, it is equal to the true value. Okay? Mu x is equal to, sorry, this is this, as n goes to infinity. Okay, so the first condition is satisfied. Let's say the second condition, consistency. Consistency condition. So right now I am looking at, the variance of mu x minus this. Okay, let me try to calculate this one. So let me write this then. This is equal to, now my estimator, 1 of n, 0 n minus 1. So this is x of n minus mu x. Okay. So I want to combine this mu x, as an argument of the summation. Combine that mu x over there. So how can I write this? So I can write this one as, instead of this, I can write mu x n 0 to n minus 1 and 1 over n over here. Since this is just a constant, it is summed n times and divided by n, I get the same, mu x result. Then, if I combine this is 1 over n, and 0 to n minus 1, x of n minus mu x, I have something like this, okay? So I have to calculate the variance of this. Now the variance of mu x minus this. So I have to calculate this one. So how can I calculate that? So if I introduce, for example, something like this, 1 over n, so 1 over n, times, let me introduce a 1 transpose vector, okay, because I want to sum all of these, and this is x0 minus mu x, x1 minus mu x, and xn minus 1 minus mu x over here. Okay? Well, this is lecture number 40. I think it is clear what we mean by vector of ones. Now I have to calculate the variance of that quantity. Well, this is already a zero mean quantity, clearly. Well, this is a result of being unbiased actually. Okay, so I can calculate this one as, insert it over here, I have 1 over n square because of this 1 over n factor, because of this variance calculation. I have 1 transpose expected value of, let me say this vector as v, okay, vector v transpose and 1, okay. So what should I do? 1 over n square, so I have vector of 1s over here, then vector of 1s over there. So how about this? Again, I have this time. This is not the autocorrelation matrix, but the covariance matrix. The reason is, mean can be non-zero as you see. I'm subtracting the means. So this is the covariance matrix, Cx0. Okay? This times that. Cx, let's say, is it 1 minus 1? Cx minus n minus 1. Let me write bigger, Cx minus n minus 1. Okay, I have something like that. So what is this one? This is Cx of minus, Cx of k, let's say, which is equal to expected value of x of n minus mu x times x of n minus k minus mu x. Okay, I'm subtracting the mean, and obviously from our earlier knowledge, this is our x of k minus mu x, this. Okay. Again, for zeroth lag, we have the familiar result, x squared, expected value of x squared minus mean squared is equal to the variance. Okay, we have things like that. So this is for this one, for k is equal to minus 1. Okay, in other words, I'm multiplying this and that when n is equal to 0, let's say n is equal to 0. Since this is Weisstein stationary, n is not critical, only the difference between the lags is important. N is equal to 0, k is equal to just 1. Okay, no, k is equal to minus 1, this is correct, because there is a minus here. That is it. So for the second one, I have Cx1. This is Cxn minus 1. This is Cx0. Cx, this is minus n minus 2. This is Cx0. Okay. I have this. Let me write cx2 over here. Let me write cx1 also over here. Let me write cx minus 1 also over here. So I'm assuming a real valued process, so there are no conjugates, as you see over here. Now, the issue is, I'm multiplying this matrix from left and right by all ones vector. So what does that do? I'm actually summing up all the entries of this matrix. That will be my final result. All the entries of this matrix will be summed up. Now, I can write this as 1 over n square. Well, there is a cx of k. Let me write this and then explain. Okay. Am I going right? Let me see. I have minor mistake over here. Okay. So what is going on? If I sum all of the entries of this matrix, well, I see a cx0 over here, over there, over there. Okay. The reason is this is a Weissan stationary process, so the variance is constant, meaning that second power of this after expectation is equal to the second power of this after expectation, Weissan stationary, meaning that I have n of these in this matrix. So when k is equal to 0, I have n of them. For cx minus 1, this is the upper diagonal. Okay, this is called, the diagonal above the main diagonal. It's called the super diagonal. Okay, so we have n minus 1 of them when k is equal to minus 1. When k is equal to 1, again I have n minus 1 of them, and the last one, there is only one over here when cx, let me say this one, this is easier to say, cx n minus 1. When k is equal to n minus 1, I have only this entry. Okay, so I should count this only once when k is equal to n minus 1. So this is the way we sum up these entries of this matrix. Now, what do I have? So as you see, I'm just trying to understand the properties of a given estimator. So if I so this is 1 minus k over n cx of k. Okay. So what did I do? I have moved one over n factor inside of this, one of the 1 over n factors over here inside of this summation. So the reason I want to do this is, well, there's somewhat a nice interpretation of this function. So this is like a triangle shaped function. Okay. So this is 1 minus absolute k over n. So this is n, this is minus n, so this is n minus 1. I think it's clear, 1 over n, so this is 1. Okay, this is with respect to n. So what's going on? So this covariance function, let me write in terms of k, is weighted, as you see, with this triangle window. This is also called in signal processing Bartlett window. Bartlett, is it double T? Maybe single T, Bartlett window. Okay, or actually this is just triangle window. And I have, C covariance function samples, let's say. Of course, this is supposed to be an even function. Let me have someone over here. So this is cx of k. So I calculate again inner product of this blue function, cx of k, sequence. So with this black Bartlett window, and calculate the sum. Since Bartlett window is capturing only the samples in between minus n-1 and plus n-1, so it's only capturing this part of it. Okay? So it's essentially attenuating somewhat, suppressing this higher ends of this autocorrelation sequence, and then summing them up. That is the issue in this calculation. Okay. This is just an interpretation of this. So what is the condition? Then, actually we have achieved our result. If 1 over n, this thing, k minus n minus 1 to n minus 1, 1 minus k over n, cx of k, approaches 0. Okay, this is for consistency. As n approaches infinity, then the random process x of n is said to be mean-ergodic. Okay, meaning that I can estimate the mean in a consistent manner if this is satisfied. Okay, and clearly, you know, this is equivalent to the definition. Okay, because that is nothing but the definition. So I have written this variance in a different way, like that essentially. But what is nice is that now by looking at the covariance function of this random process x, I can say whether this, you know, mean estimation method by the sample mean will work or not, if I can calculate the summation. So let me see. So for mean ergodicity, let me write this. Then for mean ergodicity, one over n So this is equivalent to if and only if statement, mean ergodicity. Okay, I have written this one more time over here. Or let me write another very closely related, but I won't be proving this. 0 to n minus 1, cx of k approaches 0 as n goes to infinity. Okay. So again, this is an if and only if statement. So this is a necessary and sufficient statement for mean ergodicity. So what I mean by mean ergodicity? Unbiased estimator and consistent estimator for the estimation of the mean. But as you see, this is a little bit different. Why it is different? Now I have a rectangle window over here, window of all ones. Okay, and this is only for the positive part, but you know, positive and the negative part, they are actually the same. Okay, so this is half of this summation. Doesn't matter. So if positive half approaches 0, then negative half will also approach 0. It's not a big issue. So this is just a minor detail. So this is again, you know, condition for mean ergodicity. This is, let's say, condition number 1. This is another condition, or let me write necessary and sufficient condition. Another necessary and sufficient condition. This is just maybe a little easier to check, but these are equivalent, as you see. Okay, these statements are equivalent. There should be a proof for that, but since both of them imply mean ergodicity, they have to be equivalent if the statement is correct. Now there is a sufficient condition. So what does that mean? If the limit cx of k approaches 0 as k goes to infinity. Okay. Then this implies, we use another marker. This implies, so this is only one-sided as you see, mean-ergodicity. So what does that mean? Well, if this condition is satisfied, then you're in luck. What do I mean by you're in luck? Then you know that this process is mean-ergodic. So this is an implication towards like that. So please remember, we have discussed such things in lecture number 1, necessary and sufficient conditions. Okay. So if, let me write this better because it's looking so ugly. If this is approaching 0. Okay. So if this is satisfied, you have this mean-ergodicity. If it is not satisfied, you don't know whether the process is mean-ergodic or not. You cannot say anything. If this is not satisfied, you don't know anything about that. But these ones, if this is satisfied, okay. If it is not satisfied, then process is not mean-ergodic, because this is if and only if statement, it is double-sided. Well, clearly, if this is satisfied, meaning that if this summation is approaching 0, then for the summation to converge, the end part of the summation should approach 0. So this implies that. Okay? So that is one of the results. So if this is satisfied, automatically this is satisfied, and I have this mean-ergodicity. But if this is satisfied, I'm not sure whether this will be converging or not, because, you know, again, there is an issue like that. For example, you know, a trivial calculus example, sequence 1 over n has the limit of 0. So if this is like 1 over n, it cannot be, you know, let's say that it's something like that. Okay. If it is approaching 0, then we say, okay, this condition is satisfied. But summation of 1 over n's from n1 to infinity, this is diverges. So even though this is satisfied, you cannot be sure that their sum will be, you know, finite. This is called the harmonic series, and this is one of the you know, prime examples for this kind of convergence discussions. Okay, so this is basically just a sufficient condition. So then at the end, you know, given a random process, if you can calculate this covariance function and then check this. If this is satisfied, you know, this sample mean works, you can estimate the mean. If this is not satisfied, check this. If this is, then you are sure that it is mean-ergodic or not, because it's necessary and sufficient condition. So let me have an example. So process number 1, first process, let's say, and second process. So this process is, let's say this is equal to A, where A is 1 or minus 1 with equal probability, with 1/2 probability. Okay? So this is just constant. It's either 1 or minus 1 with 1/2 probability. So how do I generate this process? Do you remember at the beginning of this course we were discussing such things? There is a sample space. From this sample space, I am selecting this A parameter, and this generates this process. Okay? So there is no other reaction. Once A is set for all n values, x of n is equal to that A. Okay? For the second random process, x of n is equal to, let's say, an. An is 1n minus 1 with, you know, 1/2 probability. 1/2 probability, and it is IID, independent and identically distributed. Now this is a little bit different from the sample space. In order to generate this process, how many parameters do I need? I need many A of n's. For every n, there is a new peak. So I pick a random vector, many random vector over here. So this random vector, 1s and minus 1, is composed of 1s and minus 1s. Elements of this A of n equally likely, and they are IID, independently distributed. Now, let's see. I have two processes. So let's try to understand whether I can estimate the mean value of the process or not from this discussion. So let me erase this sample space parts also. Okay. So let me call this first process. Let me call this second process. So expected value of x1 of n is simply expected value of a, which is equal to 0. No problems. So let me look at the other one. Expected value of x2 of n, this one, is expected value of a of n, that's also equal to 0. So indeed, this is constant, okay? So this process has constant mean vector or mean function, which is 0. Then, let me calculate Rx1 of k. Well, let's see whether this depends on n or not. X of n minus k for the first process. This is expected value of a square. Am I right? So expected value of, because it's always a. So if you draw the realizations of this, maybe I should draw it over here, you get something like this, 1 or minus 1. So this is, sorry, n, x of n. You get samples from this 1 value at all ends or minus 1s. This is at minus 1. So if you have a third realization, well, it has to be either on top of this black realization or in top of this green realization. So you have basically straight lines. So if you multiply this and that, you have a square. So at the birth of this process, you can say this a is selected. But a square is always equal to 1. So this is equal to 1. Rx of k is equal to 1. So what is the Cx of k? Well, x1. Well, this is equal to Rx1 of k minus mu x square. But this is equal to 0. Okay? So this is also equal to 1. Because the mean is equal to 0. Okay, let's do the same thing for the other process. Rx2 of k. Expected value of x2 of n, x2 of n minus k. Okay. So what do I have? I have expected value of a of n, a n minus k. Again, we have two cases. When k is not equal to 0 and k is equal to 0. When k is equal to 0, I have expected a n square. Since we have done similar things many times before, I'm doing it a little bit faster. And this is equal to a of n minus k. Okay? Because they are, as I have said, IID distributed. Okay, for different indexes, they are IID distributed. Then this is equal to 0, this is equal to 0, this is equal to 1. So I get my result as delta k. Okay? So this is Rx2 of k. Then what is Cx2 of k? Well, it's again Rx2 of k, which is delta k, because it's 0 mean. Okay? Okay, now according to our results, we are done. So one of them is this, one of them is this. So if I sketch the Cx of k, it's always 1. So I have something like that. So what do you think about this one? So is the sufficient condition satisfied? Well, sufficient condition is not satisfied because this sequence for a very large lag value, it is again equal to 1, it's just constant. So what can I say? I cannot say anything whether this is mean ergodic or not because it's just a sufficient condition. But I can check this one. Well, the average of n samples of Cx of k is just constant 1. So however I enlarge this, this will be never approaching 0. So I see that this process, x1 of n, is not ergodic, mean ergodic. Okay, is not mean ergodic. Is this expected? Let's think about this. Okay, this is one of our results. How about this one? So if I sketch this, it's a much easier sketch because it has only one sample. Well, we are done. So this is mean ergodic because sufficient condition is immediately satisfied. For a large lag, this is exactly equal to 0. Actually, this is white noise. It is non-zero only at the zeroth lag and it is 0 for all others. So I see that x2 of n is mean ergodic. Okay, according to this. Okay, so let's think about this. So this sample mean operation, let me write it over here. Is actually something like this. There is a process running, meaning that you see samples of this process. Okay. And then for mean ergodicity, you say that, okay, I'll be calculating the average of these samples, these red colored samples, okay? 1, 2, 3, 4, 5. I'll be taking the average of that. Then if the process is mean ergodic, you see this realization. If you take larger and larger and larger averages, you get the true value. But please be careful that you see only a single realization of this process. So this x of n over here, this is a realization. This is just a realization of this process. What do I mean by a realization? Please remember from the sample space, you see this red realization, green realization, black realization. So these are the outcomes of the experiment processing, generating this random process. Okay? So this is, let's say, one of those outcomes of this random process that you observe. So you observe a single outcome. So there is a single outcome as you see. And you are summing up these consecutive samples and you are dividing by the number of samples for the averaging operation. Now what do you think about this? This is exactly this analysis, by the way. So for this process, if you see this red, realization, you see always ones, but you are never aware that there is a possibility of -1, okay? So in some other realization, there can be -1s. But if you see only this red realization, because you only see a single realization, you never know that there was another possible realization with always -1s and so on. So ergodicity means actually the following. So this ensemble average, meaning that, where is this ensemble average? Let me see. So ensemble average is expected value of x of n. So at a time, fixed time, you calculate the ensemble average. At a fixed time, you calculate the average of all realizations in a way. Okay? So this is mu x. So what is time average? This is called, as we have seen, ensemble average. And time averages This is what we have previously defined. You have n samples and taking their average. This is like a usual filtering operation, you can say. You know, this is like a moving average filter. Input is x of n, one of those realizations, and output is just a sample, okay, the estimator. So this is called the time average. So a process is said to be mean-ergodic if this ensemble average and the time average, they approach each other. Actually, ensemble average is constant. Time average is approaching this ensemble average. Okay? So that is what we say. So clearly, for this process, if we see a single realization, let's say this green realization, well, I don't see any evidence of any value other than -1 over here, but at some other realizations, 1 is present. So for mean ergodicity, there is this concept of these processes, if you see a single realization, let's say, in that single realization, process is visiting all of its states. Okay? So it is switching from 1 to -1 and goes on something like that. If the process is mean ergodic. If it is not mean ergodic, it's not visiting all of its states, meaning that it's staying always at one of those states, and you can never see some other states, then you are losing this mean ergodicity property. For example, for this one, well, let me draw a realization of this over here for the second process. So this is white noise, isn't it? So this is 1, maybe 1, then it is -1, another 1, -1, -1. So as you see, these processes, in a way, so black one is right now a realization. If I draw another realization, maybe it is red one. I'm just making up these drawings, but I'm just trying to make them, you know, equally likely in such a way. Okay. So if you see this black colored markings, then that is realization number 1. If you see the red colored markings, that is realization number, let's say 2. So average of these red values will be your time average. You see a single realization. Then average at a time of all of these possible realizations will be the ensemble average. This one. And we see that if the process is mean ergodic, like in this case, time average and the ensemble average, you know, they are identical as n goes to infinity. Okay? That is our main result. And no surprises that this is not then mean ergodic, isn't it? Because if you see a single realization, you know, you don't see the whole, you don't see the totality of the states. Okay. Well, that is about mean ergodicity. Now you can say that, okay, this is indeed very nice, but how about autocorrelation? Let me then say a few things about this autocorrelation. But it's also, you know, very brief, because autocorrelation is a little bit more difficult problem. Mean ergodicity. So we will be using earlier results. So this is ergodicity in autocorrelation. Now, I have this again generic estimator, Rx of k, 1 over n, 0 to n minus 1, x of n, x of n minus k. Okay? So let's assume that I am provided a realization of this random process. So this is x0, this is x1, this is x2, then the last one is x of n minus 1. So I have only this information, but this is a realization, as you see. Okay. So I have no information about others. So for this one, it's a question mark. For this one, it's a question mark. So I have finite data, as you see. So this is n minus 1. For the others, I have no idea. Okay. Now the question is, if I do this, can I estimate the autocorrelation for this process? Okay. So we have to be a little bit careful. Okay. Now let's check bias of Rx of k estimate. Okay. So this is expected value of Rx of k. Again, I'm assuming that of course process is Weisstein stationary, otherwise there is nothing to estimate. Okay, if the process is not Weisstein stationary, you know, there is no autocorrelation function with a single variable. Okay, so if I do this, I have 1 over n, k is equal to 0 to n minus 1. But I have to be a little bit careful in the summation. Maybe I should write it over here. This is, I think I have made a mistake at this point, so this is over n. Okay, n minus k. Is this correct? Okay, it is correct. So this is over n minus x of n minus k. So as I have said, I have finite data ranging from 0 to n minus 1. So this one, if you are estimating, this has to be essentially, this index should be in between 0 and n minus 1, because I don't have any information about the other ones. Okay. So this summation, in order for this to be valid, this summation has to start from k, as you see. This is always valid because from k to n minus 1, I have that. And of course, I'm assuming that k is less than n minus 1 over here. Okay? Because otherwise, you know, I have no overlap. K is less than n minus 1 is assumed. Now, what do I have? Well, if this is the case, then I have 1 over n Rx of k. Okay? So this is k over, this is n minus 1 minus k plus 1. This is n minus k over n, Rx of k. So because, take this out. So number of terms in this summation is n minus k. So we see the following. Rx head of k after expectation is not equal to Rx of k. So we see that. So let me write it over there. So Rx k is is a biased estimator. If I do this with finite data, it's a biased estimator for k not equal to 0. If k is equal to 0, then it is okay. You know, I have Rx of 0 as the result for this. Well, how about that then? To remove the bias, we can use the following. Rx of k, 1 over n minus k, 0 to n minus 1, x of n minus k. Okay? So on the differences, now I have, instead of n at this denominator of the coefficient multiplying the summation, I have n minus k, and obviously then there is a cancellation. Okay. So this is called unbiased estimator, obviously, for Rx of k. Okay. So in MATLAB, for example, in MATLAB, there is xcore, cross correlation command. So you input x vector and you state whether unbiased. There are two possibilities: xcore, x biased. Okay. So unbiased is implementing this. Biased is implementing this. Okay. So you may wonder, why are we using this biased estimator? Because, you know, bias is something bad, isn't it? So maybe we should avoid using this. Well, there is a very important reason. Okay. So being unbiased is important, but, well, how about this? Okay. The biased estimator for Rx of k is guaranteed to be a valid autocorrelation estimate. While, okay, the unbiased one, now I think it's clear, the unbiased one is not guaranteed to be a valid autocorrelation estimate. So maybe you can remember, we have also discussed this topic in lecture 22. In lecture 22, we have said that Rx of k, a sequence, is a valid autocorrelation sequence so if and only if it's DTFT. So let me write this as an estimate, because we are not sure whether it's an autocorrelation sequence or not. It's a valid autocorrelation sequence if this is greater than or equal to 0. It's non-negative. Okay? For all frequencies. For all frequencies. That is e to the j omega, this omega. Frequencies is that omega. Well, okay. So if I estimate, then let's check the DTFT of Rx of k biased estimator. So what is that one? Rx of k is 1 over n, 0 to n minus 1. I have, x of n minus k. Am I right? So I should take its DTFT. DTFT. So what's the meaning of this? Rx of k e to the minus j omega k. K, whatever available in our hand. Okay? So 1 over n. So this is x of n. So there's a summation. X of n, x of k. Okay, something like this, minus infinity to infinity. So just be careful. This is what? Well, this is a DTFT from k index to omega index, and n is just a constant for these purposes. So let me write a few results somewhere. So if x of n has DTFT x e to the j omega, okay. So what is x of minus n? Well, you just Now in this summation, you just change the variables x of minus j omega. Okay? This is also like the scaling property of the Fourier transform. Then how about this x conjugate minus n? Okay. Then this is x conjugate e to the j omega. Okay, it should be something like that. So let me check this actually. So this is x conjugate minus n j omega n from wherever available. So how can I do this? So I take the conjugate and one more time conjugate, I guess. Okay. So two conjugates cancel each other. Then I move this. This conjugate goes away. This becomes plus. Then I change my variables minus n to, let's say, m. Then this becomes again minus. This becomes minus m. And this is minus whatever available. All of these minus infinity to infinity. All of the terms, something like that. So this is then x e to the j omega with m like this. It's conjugate. I think it's correct. Okay. So how about this? This is, well, what do you think about this one? This is x of minus k's Fourier transform. But if this is complex valued, I should take this conjugate over here. Okay. Then there's a conjugate over there. If it is complex valued. Actually, this is also what MATLAB implements. Okay. In this second argument, I have complex conjugate. So this is x of minus k conjugates dtft. But it is shifted by n units, okay? So instead of n, I am writing k minus n. So it is shifted by n units. Okay, this is how we interpret this. So it is, well, we can do some calculations and see this, but it is dtft of x of minus k shifted by n samples. Then it is this. This part is x conjugate e to the j omega. Due to the shift, I have this. Then 1 over n x conjugate e to the j omega. So I have x of n, this is small x, this x, times this. So I evaluated this summation. This is constant. For the sake of this summation, it goes out. Then I'm left with this and that. And this is also x of j omega. And we see that this is indeed positive valued. Okay. So this is always greater than or equal to 0. Its dtft is always greater than or equal to 0 for all frequencies. So indeed, if I do it this way, I immediately get my result. But if I include n minus k over there, then it becomes a multiplication by a second function, isn't it? So this n minus k, and it's a very different function. So this will be the product in time domain. That will be the convolution in the Fourier domain. So I have to calculate the convolution of 1 over n minus k sequence, Fourier transform of that, with this. And that is the issue actually. Because of that, it becomes, this is not guaranteed. But for the bias case, as you see, I always have a valid autocorrelation, but it is biased. For the unbiased case, it is unbiased, but it's not guaranteed to have a valid autocorrelation. You are just, trying your luck. Okay, now this is all about this, validity, biasness, and so on. So what should I do? Now, the consistency to discuss the consistency of Rx of k estimates. We use earlier results on mean autocorrelation. So let me define, for example, a z. Let me see, what was my notation? Let me define something like the c k of n. Okay. So this is x of n times x of n minus k. Okay. So you may consider that I am interested in the mean of this. Assume k is fixed right now. K is some number, a fixed number. So the obviously expected value of this is, it's like the mean calculation of a random quantity, isn't it? So this becomes, the mean of this Zn, let's say, for a constant k. But this is also the definition of the autocorrelation. Okay? So I will be discussing the mean of this Zkn sequence, and I will try to say that if Zkn is mean-ergodic, okay, then clearly we see that x of n is autocorrelation ergodic, i.e. a consistent estimator for the autocorrelation. So right now I can immediately use my theorems. So what are my theorems? For example, a sufficient condition. Sufficient condition says the following. Then if the limit covariance of zk, okay, zk of, let's say this is L, goes to infinity, then we have the result. Okay? But here is the issue. For this covariance calculation, what do I have? I have to have the following expected value of now zk n minus L. Okay? So that is supposed to be something like this, minus expected value of zk n minus zk n minus L. Okay? So the difficulty is this part, because this is nothing but this one. So I have fourth order moments, x of n minus k. So this is x of n minus L, x of n minus L minus k. Okay? So you see that I have to calculate this fourth order moments in order to discuss this. So that becomes a little bit difficult, because even the, saying something about second order moments is, accurately saying something about second order moments is difficult. So let me write it as a sentence. So ergodicity in the autocorrelation requires the knowledge of fourth order moments because of this discussion. Okay? Fourth order moments, and therefore may not be practical to use or to check Okay, because it's in practice you don't have that kind of information. For the covariance information, if this is standard second order moments, you can expect that if these legs are very much separated from each other, they will be uncorrelated. Okay, for the standard covariance information, if for example this is equal to x of n minus k, this is, let's say, mu x, okay, x of n, expected value of x of n minus k. Okay. So if k is very large, then these two samples are very much separated from each other, and we intuitively see that then asymptotically they may be uncorrelated. Okay. So that is that for a random process x, for the mean ergodicity, that makes sense. But for the autocorrelation ergodicity, now the situation is more complicated because I have, as you see, 4 samples. Instead of 2 samples, I have 4 samples like that. So this becomes, difficult to justify. Okay? So, for example, for k is equal to 1, these 2 samples are close. The other batch of samples, they are also close pairwise, but they are, as a couple, they are very much separated from each other because of this L goes to infinity. The case is whether they are uncorrelated on this condition, the product is or not. So this is not very easy to check. But let me say, for Gaussian processes, there is again a simpler result. There is a simplification, let's say. There is a simplification. Let me see. There is a simplification to the following. So the limit n goes to infinity, 1 over n, k 1 to n, this is cx, but square, okay, is equal to 0. This implies, for Gaussian processes, double implication, necessary and sufficient. This implies ergodicity in autocorrelation. Okay, so this is if and only if, but for Gaussian processes only. The reason is, now I think you will immediately agree once I write this. Again, Gaussian processes are defined by first and the second order moments. So if you can express this fourth order moment, 4 samples, Gaussian samples, okay, samples from this Gaussian, in terms of their first and the second moments, then you can say something about this. So if I have jointly distributed 4 Gaussian random variables, I have also this. Again, not very much surprising, but this requires a derivation. Okay, so pairwise, x1, x2 pair and the rest, x1, x3 pair and the rest, x1, x4 pair and the rest, okay? So x2 and x3, they're already expressed, okay? 3, 4, already somewhere in there. Okay. So this is an equality valid for Gaussian, jointly Gaussian random variables. Jointly, let me write normal random variables. Then clearly this fourth order moment can be expressed as summation of 3 second order moments, but this second order moments are multiplied. Because of that you have a square over here, okay? Please pay attention to that square. So if this converges to 0, then you have also ergodicity in the autocorrelation, okay? So this is for Gaussian processes, I have said. So that's all I would like to say about, let me see, ergodicity. And this is also a very important and a practical topic. This is how you estimate the autocorrelation sequence, how you estimate the mean value, etc. And depending on the cases, you may have difficulties. Please be aware of that. So this is somewhat something to keep in mind. Okay, thank you very much. So we have only 2 lectures left. We will be discussing best linear unbiased estimators in the next lecture. Okay, thank you very much.